All right. How's it going, everybody? Everybody doing good? Cool. 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 All right. Quiet down, everybody. Quiet down. I know. So excited to get this recitation going. Okay. All right. For question one, check it out. We got water at 15 degrees is being pumped from reservoir A into large tank B. The power output of the pump is 3.7 kilowatts. That's the W dot that we're going to be dealing with. We want to determine the volumetric flow into the tank when that height H right there is 8 meters. We want to include the minor losses for the elbow and sudden expansion in the tank. The pipe is made of commercial steel with length 30 meters, that diameter, that surface roughness, and we're also given the properties of the water. So the only other thing I really want to write down is on an exam or something, we'll give you a table full of minor loss coefficients, right? But here we don't. So we've got this elbow right here, right? Elbow, elbow, and then we've got this expansion thing right here. Okay. So our minor loss coefficients, so K elbow equals 0.9, and then K, I'll say EXP for expansion. It's just 1.0. And we'll give you like a table of these, like, if you've got a big, really complicated problem with all sorts of twists and turns and stuff, we'll just have a table full of the different ones with the corresponding values. So don't worry about that. But, okay, so first off, whenever you see some sort of pumping problem, we want to write out our Bernoulli's equation straight up. So we're going to have limits equals same thing on the other side, pretty much. Right. And so I always like starting with that. I'll almost always start with either the Reynolds number or this equation. And it's kind of nicer to start off with the Bernoulli's equation first so you can see what cancels and what you end up having to really solve for. Because if everything ends up canceling really well and you just get everything in terms of stuff you already know, then it's pretty easy. But anyway, let's start canceling stuff out. So both of these, so this is point B up here. We'll call that like point A right there. So point A and point B are both open to atmosphere. So we can take gauge pressures, cancel out those pressures. We can also say the velocity at A and the velocity at B are both zero because it's like, we're dealing with a bit, it's like a lake right here, and then we're a giant tank, right? So those are zero. And then do you guys know about like those alpha terms, alpha A and alpha B? Do you know what those are? Um, that's just like the turbulent flow parameter thing. Alpha is one if it's turbulent, and alpha is two if it's laminar. Obviously, in this case, we don't care because the velocities cancel out to zero. But that's all it is. If it's turbulent, alpha is one. If it's laminar, alpha is two. That's it. Anyway, uh, we're gonna take the height of A, as our datum point, so ZA can go away. Um, and then we have some H pump, right? We've got some pump work going on. That's where that comes from. But we don't have any turbine, so that can go away. So our equation simplifies down to H pump equals ZB plus HF. And so now you go, all right, well, that's pretty easy looking equation, but there's a lot of stuff we don't know, right? In order to calculate HF is our head loss stuff, right? Where HF equals HF major plus HF minor. right? In order to calculate those, we need to know some velocity, right? Because we know HF major equals F L over D V squared over 2G. HF minor is the sum of these KLs, these minor loss coefficients, times V squared over 2G. Where V squared, that the V's we're talking about throughout this problem that don't have any subscript, that's like the average velocity inside the pipe, right? We're just, for simplicity, we're assuming there's no like velocity gradient inside the pipe. It's just a constant average velocity. And so, all right. So we go, well, we don't know anything about these, okay? And for F, we presumably need Reynolds number. So what we're gonna do, this is actually, I didn't mention it to start off, but this is the hardest type of problem you can get with these, where you need to find some volumetric flow rate, but you're not given any velocity, any flow parameters like that. This is as hard as it gets. So what we want to do, solve for every. pump. Where are we at? So I'm going to plug into this bad boy right here. Right, where our ZB is that 8 meters we were talking about from the jump. So we've got, so what's our H pump equal? H pump is W dot divided by rho G times V pi over 4 D squared equals ZB is 8 plus our HF is just the minor and the major added together. It's 20.3874 V squared FV squared. V squared F, same thing, whatever. Okay. And obviously, like, you'd have this, the rest of these numbers, the W dot is 3,700, right? Right. Um, so now the only thing you don't know on this left side again is that V. So what we want to do is you can see in this thing, right? We've got two unknowns and only one equation. So what we can do is we can program a big MATLAB script that can iteratively solve both of these things using the Tolbert equation and the Reynolds number. Okay. Yeah, it sucks. Yeah, it really sucks. We never make you do this by hand. All right. This one's purely for homework or recitation purposes. Even on my T, it says like, using MATLAB, go do blah blah blah. Yeah, like I can do a basic one by hand, not too bad. I'll show you in problem 2 how to go about doing that. But doing one like this by hand would be super, super tedious, super taxing, and it just wouldn't be that big of a deal. Um, so what we want to do, um, set equation equals 0 and simplify. And we want to do that because if we set everything equal to 0, we can go in MATLAB and use like F0 command, some sort of iterative solver, right? Numerical analysis stuff. So when you do that, you end up getting this kind of sort of ish final equation that computers really like in this form where 0 equals 20.3874F plus 0.09684. And this is multiplied by v cubed. And v cubed because this v down here, you end up multiplying that over, right? So you can factor out a v cubed, right? You have a v cubed there. Plus 8v minus 85.4413. Right? And so this is the equation we really want to be solving. So I'll put a box on that. So now solve iteratively. Ooh. So solve iteratively using, did I spell iteratively? Is there two T's in iteratively? Or is there just one T? I don't know. All right, whatever. I'm not an English major, whatever. Um, whatever. Yeah, so you solve this iteratively using Colbert equation and the Reynolds number. Are you guys familiar with the Colbert equation? Okay, cool. I'll write it for kids online. I'll write it down. But Colbert equation is 1 over, and this is my notation for it. I like writing F nu equals, -2 log. It's actually my favorite way to solve stuff like this. So anyway. And so, to solve this, you would pick an F0, right? Pick an initial F, calculate this right side, solve for F new, right? And then rinse and repeat. Use that F new, plug that into the right hand side, go repeat, yada yada till it stops changing, right? And so you do that. Essentially, what you would do is what the computer would do is hit some V with that RE, hit some F0, and iterate. Stop when everything converges. Exclamation point. Much easier said than done. Um, again, use MATLAB or whatever your other favorite analytical software is. I don't care. It doesn't matter. Anyway, at the end of the day, though, you'll get this. You'll get F equal to 0.01, 0.018739, and V equal to 4.65233 meters per second. Okay. And so that's the velocity thing is the important one. And like we've got a lot of decimals on both these numbers. Usually I'll say like, oh, I don't care, like lop it off at like 2 decimal places, whatever. For the friction factor stuff, try and carry as many decimal points as you can reasonably keep track of. Small variations will have a pretty decent sized impact on the final answer. So don't be lopping it off at like 0.01. That would be really bad. Or just like stop at 0.02. Like don't do that. Carry it out quite a ways. But anyway, so we want the volume flow rate. So plug into Q, right? Q equals V times A. We know our diameter. So Q ends up equaling 0.0205 cubic meters per second. Cool. And I feel like this is kind of a bad problem to start off with because it doesn't really give you a good idea of like how to go about using Colbert equation. Whatever, for what it's worth. Um, but yeah, there's two ways to solve problems like these with, when you have to find a friction factor. You can either use the Colbert equation, like I really prefer using, or you can use the Moody chart. Who guys talked about the Moody chart? Okay, I'll tell you why I don't really like the Moody chart. For two reasons. One, as a grader, right? It's tough for me to give you partial credit when all you say is, "Oh, I used the Moody chart," and you write down some number that's clearly wrong, right? What do you want me to do about that, right? So that's why I like the Colbert equation in the sense that if you get the wrong friction factor, at least I can see where you did the wrong calculation, and I can see like you didn't just pull a number out of thin air. You kind of knew what was going on. So that's why I like the Colbert equation from at least like that aspect of it. And I like the Colbert equation too, just from a practical point of view. The Moody chart is a log plot, or similar. Like the axes are kind of weird, and like the human brain isn't good at doing like logarithm stuff. We like linearity, right? It's kind of hard to go and trace a log plot, right? It's just funky for our brain to think about, and so you already kind of make more errors than you would want to. And I just prefer letting my calculator take care of work for me, right? I don't want to have to sit there and draw lines on a chart all day, but whatever works for you. Just know like as long as you get within the ballpark, you'll be fine anyway. All this stuff is pretty empirical. It's not like there's a real derivation heavy basis for a lot of this stuff, at least for the turbulent case. In the laminar case, there's good like closed form solutions for stuff, but turbulent flow is inherently empirical. So take it with a grain of salt. Just get within, get ballpark. So anyway, any questions for that before we move to problem two? Problem two is much more like applicable to what you actually see on an exam. Cool, cool, cool. All right, moving on. Okay, and the only bad part about problem two is there's a lot of mixed units. So I'm gonna do a lot of unit conversion stuff just straight from the jump. I'll also redraw this. The P doesn't have like a drawing for it, but I'll draw it. So I know we've got oil of specific gravity 0.88 and kinematic viscosity of that flows at 400 gallons per minute through a 6-inch diameter asphalt cast iron pipe. Pipe is half-mile long and slopes upward at 8 degrees in the flow direction. Compute head loss in feet and pressure change. So we're not dealing with any pumps or anything. No pumps, no turbines. We're just assuming that's like out of the picture, right? Maybe it's super far upstream, super back, whatever. Who cares? We're just dealing with the actual flow. Okay. So let's draw this. So we got something like this. We've got it sloping up at 8 degrees, right? And this has some length L and some diameter D. And also gives us cast iron pipe. Again, we would have like a table full of these parameters. Um, that would help you go and like trace them. Like we give you like, oh, if the pipe is aluminum, right, it would correspond to this value. If it's stainless steel, it'd correspond to this. If it's normal cast iron, it's this, yada yada. So I'll just write it for you though. Epsilon is 0.004, 0.1234 feet, I believe. I didn't change it, so I imagine it's feet. All my answers were right, so whatever. See what else. I'll do some unit conversion stuff. So we also know row of water is like 1.92 slugs per cubic foot. So with that, let's just straight up find the density of oil. Um, that will be just multiply 0.88 times 1.92. Let's also get rid of this square meters per second. Let's still do the conversion for it. Convert square meters to square feet and, make it happen. We got 4.303336 times 10 to the negative 4 square feet per second. And again, let's convert gallons per minute to cubic feet per second. Again, you can just, I would write this stuff down on like your cheat sheet. For all intents and purposes, you can just go use like an online calculator if you're doing your homework and you do this stuff. But Q is 0.891206. Oh, what the heck am I doing? Jeez. Oh, 6 cubic feet per second. Okay. Let's see what else do we need. That should be everything for now. So first off, again, let's redraw so we're gonna want some sort of pressure change, right? Pressure change and head loss is what we want. So let's do Bernoulli's. So we got all right. So now, like I said, we don't have any turbine, we don't have any pump. ZA, we can call that 0. We cannot cancel the pressure terms, right? We're solving for that delta P. So leave those there for now. But we do know, since we're assuming it's, the uniform velocity inside this pipe, right? There's no velocity gradients or anything. We can say VA is equal to VB all inside of this pipe. So once you move those over, those get rid of each other. Okay. So essentially what we're left with, let's move the PB to the other side. So we're left with PA minus PB, that delta P over rho G equals ZB plus HF. Cool. Everything good from there? Hold on. Okay, and so now we don't care about any minor losses. There's no bends, there's no twists, there's nothing like that, no expansions. So HF is simply HF major, which is F L over D times V squared over 2G. So you go, okay, so let's find our velocity first. Um, we know V equals Q over A. We know Q, we know A because we know our diameter. So I'm getting V is equal to 4.5389 feet per second, right? No, put dotted dots on that. Okay, so now we found that. To find our F, we need our Reynolds number. So let's do that. Where we just found our V, we know our diameter, and we know our kinematic viscosity. So it's 5273. And it's dimensionless, of course. And for the record, that's turbulent, right? It's above that 2300-ish number. So whatever. In this case, we don't really care. Well, I guess we kind of care. Because if it was laminar, we could use the laminar equation for the friction factor, which is nice closed form solution. It's really simple, but it's turbulent, so we have to use the Colbert equation. Or Moody. If you just go and trace the Moody chart, whatever. What's up? No, I was gonna say, there's a third one that they rarely teach. Yeah, the Holland equation. You can. I don't know it off the dome. I was never taught it. Every now and then I'll see someone bust out. I'm like, and I recognize it if you write it, but I never use it. I just use Colbert equation. Yeah, it's fair game though. It's all empirical stuff anyway. If you have a textbook that has a weird different equation I've never heard of, as long as it's the right number, it's fair. As long as it comes from a legit source, it's fine. It's all empirical. Just get in the ballpark and you'll be good. Um, anyway, so like I was saying, important that's like log base 10, right? That's not like natural log. Some people get that confused. If I meant natural log, I put an ln. Damn it. Okay, so what you do, pick an F0, solve right hand side, right? You spits out some number, right? Use this to find F new. F new becomes F0. And you just repeat. Repeat, repeat, repeat. Repeat, 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 and then you stop until it converges. Stop when it converges. And, you know, converges is a loose term, right? When do you stop? I would say to 3 or 4 decimals tops. I'd say four. Four is pretty good. Say 4-ish decimals. Question mark. I mean, if it's like, if you do this like 3 or 4 times and it's like super steady the whole time, then you can stop. But if it's still kind of moving around on you, just take a couple of steps. Once you really get in a rhythm doing the 12 equation, it doesn't take long. You just plod, 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 and it's really not bad. So if you have to spend an extra 45 seconds doing another iteration, just do it. You'll have plenty of time. But anyway, doing so, doing so, you get F equals um, 0.03773. Oh, and I always forget to say, a really good a really good guess for F0 is usually 0.02. Okay, pick F0, and I'll say usually F0 is about 0.02. All right, can you guys see that? F0 picking 0.02 is a really good guess. It'll almost always be in that ballpark. Like, our final answer is 0.03 and change. The low end, you'll get point 0, high point 0.01s, like the last one was like 0.018 or something. High end, you'll get 0.05 tops. So if you pick 0.02, you're gonna converge pretty quick. Um, Technically speaking, I think you could plug in like a million and it would get you there eventually. It would just take a long time. But, with equations like this, there's like, fall off a cliff points, right? In terms of convergence and stability stuff. So don't pick a stupid number. Pick like 0.02 and you'll be good. All right. So now what are we doing? So plug into HF, right? Where we know HF equals F L over D V squared over 2G. So plug that in, and for the record, G equals 32.2, feet per second squared, because we're in freedom units, right? So HF should get you about 63.72. This is in feet again. So step one accomplished. Step one, answer one. So now we want to find delta P. Well, from up here, right, we've got this equation. This PA minus P, that is our delta P. So we can say delta P equals, it's just rho G times ZB plus HF. And we know rho and G, and we know our ZB, or we know our HF. So what's ZB? Well, ZB is just the length of the pipe times sine of the angle it's tipped up. So sine 8 degrees. All right, plug everything in. Delta P is somewhere around 23,700. PSF, pounds per square foot, or if you prefer, SIMDIF. And I say around 23,700 because obviously it kind of depends on where you stop iterating, right? Whatever your little decimal is, it's going to be wishy-washy. Ballpark. Everything with stuff like this, it's all ballpark, okay? So if you and your buddies compare answers and you get, oh, I got 65.2. Oh, I got 62.3. Hey, it's fine. Just depends on where you stop. As long as you don't get a bajillion, a million, trillion, you're fine. So like on a physical basis, the way I think about it, nobody's ever corrected me. If anyone's watching this video online this far, nobody's ever corrected me when I say this. But from a physical basis, what I think about it is like that loss, like we're losing 63.7 feet of like potential pumping ability. That's what I think about it. Yeah, that's what I think about it. I don't know if that's actual physical meaning, but it gives me a good sense of what's going on because it's a friction thing, right? And so I'm like, in order to balance this Bernoulli's looking equation, I need that 64 feet on the opposite side. So I'm like, okay, well, that means it must have been able to push like an extra 64 feet if it wasn't there, right? So that's why I think it helps me sleep at night. I don't know, whatever, it doesn't matter. But from a physical basis, that's how I always think of it, for what it's worth. Anything else? Anybody? Anything else to say? What's up? Okay. Oh, you don't know any. Okay, so if you just look at the equations themselves, right? Um, so F major, right, is some friction factor, which is a parameter of like the pipe itself, right? We went and had to solve for that, times the length over the diameter, right? So the length to diameter ratio, times basically its velocity, right? And so the major loss part of the loss equation is only a function of like really the length of the pipe, right? If you have a really long pipe, you're going to have larger major losses. Where on the flip side, if you go back to the minor losses, it's that those KLs, those loss coefficients, multiplied by basically the velocity, v squared over 2g, right? Um, so that's more a function of the bendiness of the pipe, right? So if you have a really long straight pipe, you're not going to have really any minor losses. If you have a really curvy short pipe, you're going to have a lot of minor losses and vice versa. And so, like I said, we call them major and minor losses kind of arbitrarily because if you have a short, curvy pipe, those minor losses could be way bigger than the major losses. We just call them major and minor because typically you'd like to plan to have a straight pipe that's really long compared to a short pipe that's all curvy. And from like a physics point of view, those minor losses come about because obviously as you accelerate water around a 90-degree bend, you lose a little bit of energy, right? You don't get it for free going around that bend. So that's where that comes from. And we just call those major losses and minor losses. That's all you got to know. It's not too bad. But yeah, good question. You guys really didn't talk about anything about that? All right. Oh, that's fine. Well, that's literally this is as hard as it gets. This is the major loss equation. And when you don't have any minor losses, right? Like we said here, it's just a straight pipe, so there's no minor losses. Then that's all you have to do for the head loss stuff. Where you just find this F, find a velocity if you need to, and plug and chug. But yeah, but that friction coefficient, that F, is obviously a function of like the parameters of the pipe roughness kind of thing, but to a kind of lesser extent, because you also have this Reynolds number floating around in here. So anyway, you know what I'm talking about. Cool. Anybody else have anything to say? Very cool. Sweet. All right. As usual, if you got any questions, shoot me an email. Without further ado, all right. Have a good one.